This is problem 50 from chapter 15. A boy A having weight of 80 pounds and a girl B having weight of 65 pounds stand motionless at the ends of the toboggan, which has a weight of 20 pounds. If A walks to B and stops, and both walk back together to the original position of A, determine the final position of the toboggan just after the motion stops. Neglect friction between the toboggan and the snow. So the forces that we have acting on our system, which includes the toboggan and the two people, are the normal force and the force of gravity. There are no forces in the horizontal direction because there is no friction, so the impulse in the x direction is 0. There are two equations that we can use for impulse momentum. We have equation 15.3 and we have equation 15.6. In equation 15.3, this is the mass times the velocity of the center of gravity plus the impulse here. In equation 15.6, we have the sum of the momentum for each individual object in the system. You can use either one of those equations for this problem. Remember that from page 254, they tell us that the mass times the velocity of the center of mass is equal to the sum of the momentum for each object in the system. So that's going to be important to us later on. And so initially, everything is at rest. So the initial momentum, if we use the velocity of the center of mass, is 0. But because there is no impulse, we have 0 for the initial momentum plus 0 for the impulse. So the final momentum must be 0 also. So that means that for the whole time, the momentum must be equal to 0 because there's never any force acting in the horizontal direction. So we can use equation 15.6 and we can write the final momentum as the sum of the momentum for each of the three objects. That gives us this equation here. But at any moment in time, the velocity must be equal to 0. So rather than doing the instantaneous velocity, we can do the average velocity. If we do that for the center of mass, it must always be equal to 0. If we do it for the three objects individually, the sum of the momentum of each individual object must be equal to 0. So writing this out using the average velocity gives us what we have here. And whatever delta t is, it must be the same for all three objects, so we can multiply both sides by delta t, and so cross that out in the denominator. What this equation tells us is that the location of the center of mass cannot change if we do not have any forces acting in the x direction. This problem is similar to the situation that you would have if there are two people standing in a canoe in a still pond. So if one person walks towards the other side of the canoe, the whole canoe is going to move in the opposite direction. So in this problem, we have person A moving towards person B, and then they both move it back to where person A was initially at. But because person A goes this way and then back again, we can ignore the fact that person A is moving because they're starting in the same place that they ended from. So before, we have the two people standing 4 feet apart, and we can pretend that person B is just moving towards person A, and we can keep person A in the same spot the whole time. So afterwards, we have something like this with A and B in the same place, but the whole toboggan has moved to the right. So person A is in the same spot relative to the toboggan, but person A actually moved because they started off here initially and they moved a little bit over here, but they did not move relative to the toboggan. Okay, so now we want to go to our equation up here, and I'm going to put a link in the description which talks about how you find the center of mass, so that's similar to the equation that we have here. Okay, now the tricky part is person A and the toboggan actually moved. Let's call this distance here x. And the whole toboggan and person A both moved the same distance. Now, person A actually moved here and then back here again, but we don't really care about how person A moves relative to the toboggan because they're going back to their initial point on the toboggan. So we can take this and this. The displacement for person A and the displacement for the toboggan is the same. So 0 is equal to mass A plus mass of the toboggan times, it can be called that x here, okay? So let's say delta XA, delta XT, they're both equal to x. Okay, now we have the term here from person B. Person B moved this way in the negative direction. The distance that they moved from here to here is 4 feet, but they didn't actually end up 4 feet from where they started from. They ended up where person A was, and since the whole toboggan moved this way, the distance from where person A started from, I mean, the people are supposed to be in the same place, but this would be 4 minus x, but that's in the negative direction. So this would be minus the mass of person B times 4 minus x. So we have mass of A plus mass of the toboggan times x is equal to the mass of person B times 4 minus x. And we want to solve this for x. Person B has a weight of 65 pounds, so this would be 65 divided by 32.2. This is 4 minus x. And person A and the toboggan together have a weight of 100, so a mass of 100 divided by 32.2. We have x here, we have 4 minus x here, we have a 32.2 in the denominator on both sides, so we can cancel that out. And then we can say 100x is equal to 65 times 4 minus 65 times x, and then we have 100 plus 65 times x divided by, oh, never mind that. 100 plus 65 times x is equal to 260. So x is equal to 260 divided by 165, which gives us 1.58 feet. And that's your answer. So this problem was a little bit different than the other problems in this section. And you can think about it in terms of center of mass and check out the link in the description section for more on that.